So I want to delve a little bit deeper into why these polynomials act like these functions so well. So you saw in the last video we were dealing with p sub 5 of x, and the 5 meant the degree, the highest degree term. So the highest degree term in that was the 5th degree. Well, there's also, as you can guess, p sub 1 of x, and there's p sub 2 of x, just whatever the highest degree term is in there. Well, our tangent line, our line in the plane that acts just like our function, is p sub 1 of x. It is to degree 1. So it's got an x term in it, and it is a line. So p sub 1 is a line in the plane that acts just like our given function at and very, very near the point of tangency. The point around which our polynomial approximation functions are built is the point of tangency. In our last example for p sub 5 of x, it was built around x equals 0. So very near x equals 0, it acted just like the function. It acted like it linearly, it acted like it quadratically, cubically, all the way up to the 5th degree. So for any function f of x, the tangent is a close approximation of the function for some small distance from the tangent point. Here we have f of x equals f of a. If we have p sub 1 of a, the line that acts just like the function, and we forced it to be that way, near the point of tangency x equal a, then we're guaranteed very, very near that point of tangency. If we zoomed in and that's all we could see, it would look like that our line and our function had the same behavior. But you can see the further and further and further away we get from that point of tangency, error is introduced. There's over approximation by the line. The line gives us a higher output value than the function does at whatever that x value is to the right of a, x plus some distance from a. Okay, here the output of the line is still an over approximation, not an under approximation. So the output of the line would be higher in the plane to some distance to the left of a. Some distance to the left of a. So the further and further away we get from that point of tangency, the less and less and less accurate our first degree approximating polynomial will be. So how could we get that better? Well, we could get it to be a better approximation if our approximating polynomial shared the same concavity. Now, we wouldn't necessarily be accurate, very much further away, but it would buy us a little more accuracy if the concavity were the same. So when we approximate what's happening on a function with a line, then that is the linearization of the function. Very near the point of tangency, how does the function behave according to the line? Well, here's what p sub 1 of x looks like if we've built this first degree polynomial very near our point of tangency. And in general, we're going to call that point of tangency x equal a. So at x equal a, we said before, we're going to force the outputs of the functions to be the same. So f of a, we're going to force to be the same as p naught. Need to slow down. As p naught. Okay? So here would be p naught plus our first degree term. P sub 1 is actually p naught plus the first degree term. Not really p sub 1. So p sub 1 of x is p naught of x, the output of the function, plus the first degree term. And I don't know if you can follow me here, but if I have the point of tangency x equal a, I'm going to call that x sub 1. If I plug a into my function, that's going to get me my output f of a. I'm going to call that y sub 1. So now I have a point, x sub 1, y sub 1. And if I take the derivative of my function and evaluate it at the point of tangency, that gives me my slope. And with a slope and a point, I can find the equation of a line. It is y minus y1 equals the slope times the quantity x minus x1. So if I plug all those values in, y minus y1 equals the slope times the quantity x minus x1, and I solve that for y, in other words, add f of a to both sides, hopefully you can see the equation of the tangent line in this polynomial approximating form. So this is just derived from the point-slope equation for the equation of a line, and using A, our center point around which we're building our polynomials, as the point of tangency. So linearly, that's what's going to be happening. So we've discussed repeatedly we like working with polynomials because they are pretty functions. They behave nicely under all evaluations. The only evaluations mathematically that we have to worry about, operations, are addition, subtraction, multiplication. Division is just multiplying by 1 over. So really there's only 3 operations mathematically we have to worry about. If a linear polynomial gives a certain approximation to a function, we would expect a quadratic, a curved graph, to give a better approximation of a curved function. We would further expect the cubic polynomial to be even a better approximation. And as I explained a while ago, what that's going to do is buy us further and further and further distance on either side of our point of tangency, where our approximating polynomial acts just like our function. So since this is true, we're going to want to find the polynomial of degree n that is the best approximation to the function near the point of tangency. And by best, I mean the polynomial that will allow us to get the acceptable error in the output value of the polynomial in relation to the output value of the function that we're approximating. So by best, I mean least error. And by degree n, I mean, in our first example, we built the polynomial to the 5th degree that would mimic the function. We can build these polynomials to degree n that will mimic the function. So as we've said before, the significance of linear approximations is that we can count on 2 things: that the outputs of the approximating polynomial at the point of tangency equal the output of the function, and that the slope of the approximating polynomial equals the slope of the function at, and therefore very near, our point of tangency. Quadratically, we get those things in P sub 2. The outputs are the same, the slopes are the same. When we build P sub 2, we'll see, just like we did a while ago, P sub 2 of x equals P sub 1 of x plus the next term, the 2nd degree term. Second degree term. So all of these P sub n of x's include the prior approximating polynomial terms already in them. And we'll see that as we build some approximating polynomials. So here is what the quadratic approximating polynomial, or the Taylor polynomial of order 2, based at a is. P sub 2 of x has P naught plus the 1st degree term. So that is P sub 1 plus the 2nd degree term. And that whole thing is P sub 2 of x. And you can see, here's our line, the output of the function, plus the slope. This is y equals y sub 1 plus the derivative, the slope at the point of tangency, times the quantity x minus x1. The next one is the 2nd derivative evaluated at the point of tangency, divided by 2, times the quadratic term, x minus the point of tangency, quantity squared. So just as in linear approximation, we have a corresponding quadratic approximation. What if we added more terms? What might P sub 3 of x look like? Well, let's follow this pattern. It's going to have P sub 2 in it. It's going to have f of a plus f prime of a times x minus a. There's p sub 1. Here's p naught. Those two together are p sub 1. We add the quadratic term. All of those together are p sub 2. So p sub 3 is going to have the third derivative evaluated at the point of tangency times the quantity x minus the point of tangency cubed. Now this is not quite as obvious, and we'll see as we go along here. This is actually going to have 3 factorial, or 6, as a denominator. P sub 4 would be p sub 3, what I have written there, plus the fourth degree term. We would take the fourth derivative. We would evaluate it at a. We would divide that by 4 factorial, which we're going to see equals 24, times the quantity x minus a to the fourth. So you see a pattern. We can build these polynomials really easily just by following that pattern. And a Taylor polynomial p sub n of x of order n, order means the degree, is chosen so that its value and first n derivatives at x equal a, and a is the point of tangency, agree or match or equal those of the function we're approximating. We'll see that p sub n also has degree n, unless the coefficient of the nth term is 0. Taylor polynomials usually fit their target functions better and better and better as their order increases. So like our first example, if I said we want this 5th degree Taylor polynomial to approximate our function within, let's say, 5 decimal places of accuracy, very near the point of tangency, well, if it doesn't, then we just add another term. And we continue to add terms until we get the amount of accuracy or the value of error that's acceptable. So this you need to know. This goes in your notes. Here is the formula that we're going to use, and you need to be able to readily bring this up. In other words, this needs to be memorized. But you'll see that it has a pattern that's very easy to memorize. So p sub n of x, the nth degree Taylor polynomial that approximates our function at a, our point of tangency, has the form f of a plus f prime of a times x minus a, plus the second derivative evaluated at the point of tangency, divided by 2 factorial. 2 factorial is indeed 2. Times the quantity x minus a squared. And we continue that pattern. Third derivative at a over 3 factorial times x minus a cubed. Fourth derivative at the point of tangency over 4 factorial times the quantity x minus a to the fourth. And we continue that pattern all the way up to the nth degree. It's the nth derivative evaluated at the point of tangency x equal a over n factorial times the quantity x minus a to the nth degree. Now, they'll either tell us the degree of the polynomial they want us to build, or they'll tell us the acceptable amount of error to within how many ever decimal place accuracy, or they may even give us a fraction to within 1/10,000th. Recall, hopefully from Algebra 2, if not from pre-calculus, that n factorial just means starting at the value of n, you have the product of how many ever integers starting at n and multiplying by n minus 1 all the way down the line. So for instance, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. All right? That would be what 7 factorial looks like. You understand, you just multiply by the next smallest integer all the way down to 1.